next video, this one is the introduction to exponential functions, even though I know we started this in class the other day. And we'll probably continue working on it a little in class after we do the stuff from the video. There will also be a second video to talk about later. The goals here: being able to recognize an exponential function when you see it in the data. Identify the roles of the parts of an exponential expression, so the algebraic expression there, different numbers involved, you should know what each one does. When you see an exponential, you should be able to tell from the equation whether it's going to be showing growth or decay. And finally, you should be able to find the base of an exponential if you know what the growth rate is, and vice versa. If you know the growth rate, you should be able to find the base. Alright, so something we did in class. We reviewed the fact that linear functions show repeated addition. That's called the slope. So in 2x plus 7, y starts at 7, that's its initial value, or also known as the y-intercept. It's called initial value sometimes because in a lot of these things, the x is measuring time. So when time is 0 is the starting point. And the y is increasing by 2 each time x goes up. Notice, however, we might be adding over and over, but it shows up in the equation as 2 times x, because repeated addition is just multiplication. That's something that hopefully your elementary teachers way back in the day tried to stress to you. Multiplication is just repeated addition. Now, these things called exponentials. That's what happens when you are multiplying over and over and over. Repeated multiplication shows up as an exponent. These are called exponentials because the variable then is in the exponent. We also looked at the general form of these. Y equals a times b to the x power. This time, a, the number in front, is your initial value when x is 0. That's because anything to the 0 power is just 1. So b to the 0 is 1. A times 1 is just a. So this is the number you start with. The base, b, that is the number that's being multiplied over and over and over again. X turns in, this time, to the number of times you're going to be multiplying b. Brief talk of this. When we start getting into the applications, sometimes b and sometimes x, the exponent, are based off of some formulas, and rather than having a formula for b, a formula for x, and then you put it into a times b to the x, they'll combine all of it. So it'll be a and then parentheses, whatever the formula for b is, close the parentheses, and then the exponent, they'll put the formula for x. And you'll see that when we get into the exponential, or into the application problems, probably in the next section or two. Well, no, I know for certain it's going to be in the next section. But regardless of how complicated it looks, it will always boil down to an initial value, some base, and an exponent that's going to tell you how many times to multiply that base to the initial value. Okay, I have 4 exponentials listed here. And I have their values for when x equals -3 through 5. I want to pause the video for a second, look over these numbers, and just kind of see what's going on. Because for the sake of time, my explanation is going to be kind of brief. Alright, the first two, 2 to the x and 4 times 2 to the x. Notice they both have a base of 2. And if you look, 1/8 times 2 is 1/4, times 2 is a half, times 2 is 1, times 2, times 2, same thing here. Half times 2 times 2 times 2 times 2 times 2. If you go the other way, decreasing x's, 32 divided by 2, divided by 2, divided by 2. That's why a negative exponent gives you a fraction, by the way. 1 divided by 2 is a half, divided by 2 is a fourth. Something you should notice is these two have the exact same values in them. They're just at different x places. And that's because of the initial value. There's no a shown here. So it's a 1 times 2 to the x. So when x is 0, you get a 1. That's where it starts. This has an a value of 4. So when x is 0, it starts at 4. So they have a different starting point, but their behavior is the same, multiplying by 2 every time x gets bigger. These two particular ones have the exact same y values. They just happen for different x's because the starting point was different. Third column has the same starting point, 4, as the previous column, but this time the base is 3. So you look, they start at the same point, but instead of multiplying by 2 each time, they multiply by 3, 12, 36, and so on, multiplying by 3. And when you back up going the other way, divide by 3 gives you 4/3, divide by another 3 is 4/9, and so on. So notice the roles of what's going on here. The initial value, 1, 4, 4. The behavior, these cases, the base is 2, multiplying by 2 every time. In the third case, the base is 3, multiplying by 3 every time. So kind of see how that works for the final column. Initial value is 8, so when x is 0, we have an 8. And this time our base is a fraction, 1/4. So when you multiply by 1/4, you're going to get smaller. So 8 times a fourth is 2, times another fourth, times another fourth, times another fourth. It gives you a smaller and smaller and smaller fraction in that direction. Meanwhile, going the other way, dividing by a fourth is the same as multiplying by 4. It'll go bigger that way. I know here this first year, as I'm making the video, we talked about the graphs and showed some of the graphs in class already. And otherwise, we'll do the graphs and kind of show the behavior visually in class anyway. All right. That base is going to be a positive real number. No imaginaries from like we did in the quadratic section. And we're not going to deal with any negative bases. We're going to keep it nice, fairly simple here. Now, from that table on the previous slide, if that base is greater than 1, like the first 3 columns, that's showing growth. As x gets bigger, the y value gets bigger because you're multiplying a fairly big number. If that base is between 0 and 1, remember it has to be positive, so it has to be bigger than 0. But if it's less than 1, like that last column where it was 1/4, you multiply by a fraction like that, you're going to get smaller and smaller and smaller. That's called exponential decay. So in the next slide, I think we have a couple examples of some exponential functions, and we just want to know whether it's growth or decay. So 100 times 0.12 to the x power. This is our initial value. We're starting at 100. This is our base, 0.12. Well, 0.12, get the pen here. 0.12 is less than 1. I'm not going to write that anymore. I'll just talk about it. But anyway, 0.12 is less than 1. So that is a decay. That's supposed to be a D for decay. So that's going to get smaller and smaller and smaller. Where is it? All right, the next one. 0.2 times 5 to the x power. Here's our initial value. This is our base. That's what we're interested in for this one. 5 is bigger than 1. So it's going to get, supposed to be a G for growth. It's going to get bigger and bigger and bigger. It's growing. Again, initial value. This thing will start at 16 when x is 0. And we're multiplying by 1/2 each time. So it's getting smaller, decaying. All right, next goal. We want to get our B value, our base, from the growth or decay rate. So let's take, for an example, a bank balance that grows at 1.24% per year. That's the interest rate. That's what the bank pays you just for keeping money in the bank. So after the first year, we're going to have all the money we have currently in the bank, 100% of what we have. Okay. We're going to also get the 1.24% that the bank is paying us. So we're going to have a total of 101.24% of what we started with. Okay, 100% of what we had and the new 1.24%. That means our base is going to be 1.0124. This percent rewritten as a decimal. Just move the decimal point over like you've done for years now. I mean, percents are done, what, 6th grade or something? So that is going to be the base of the exponential. Another example. So we have a population of something that's decreasing by 5% a year. So we started with, that's supposed to be a 1. Geez. We started with 100% of what we had. We lost 5%. So we are going to have 95% left. Okay. Change 95% to a decimal. Our base is 0.95. The base is kind of telling you the percent that is remaining, or the percent that we are going to have at the end. When it's growth, that number will be bigger than 1 because we will have over 100%. That's why it works the way it does. If we have a decay and we lose something, the base will be less than 1 because we will have less than 100%. So, base value is given a rate. For exponential growth, the base is 1 plus r. That's in decimal. 100% plus our rate, change that to decimal. For exponential decay, it's 1 minus that. Or 100% minus the rate as a percent. Alright, so now, some examples of that. I'll switch over to the tablet. Record. Alright. So, first example I have here. The tuna population is declining by 12% each year. Find the base of the corresponding exponential. Alright. We're declining. That means we're decaying. It's going down. So we're going to have 100% of the tuna we have minus 12% equals, means we have 88% left. So the base is going to be, with the decimal point, 0.88. Next example. Number of raccoons is increasing by 8.7%. Increasing is growth. So we have all the raccoons we currently have, and another 8.7. So 108.7%. Convert that percent to a decimal, 1.087. There's the base. And before we move on to the other example I have already written, switch over to red. If we could go the other way with it. Let's suppose B is 1.2. Well, that's the same as 120%, which means we started with 100% and added 20%. So this is a 20% growth. If B would have been 0.8, well, that's 80%, which means 100 minus 20, so that would have been a 20% decay. So it works both directions. All right, let's kind of wrap all this up into one Neat problem to do. Population of the United States in 1994. It auto-corrected my N because it didn't understand the period was for an abbreviation. Anyway, 1994, 269 million with an annual growth rate of 0.7%. We want to find the population this year. Okay. Well, our initial value is 269. I know it says 269 million, but just to make the numbers a little easier to deal with, we're going to keep it as 269, and we just have to remember at the end that's in millions. All right, for the base, we are growing. So 100 plus 0.7 is 100.7%, which is the same as 1.007. That's changing every year. So the next thing we need to know is how much time has gone by. So X is time. And 2014 minus 1994 is 20 years. Alright, so the current population is the initial value, 269, times the base, which we figured is 1.007, to the 20 years have gone by. Type that just as it is into your calculator. 269 times 1.007 to the 20th power equals about 309 million. I'm just rounding up to the nearest whole number. So you go. That's how an exponential works. Find your initial value, find your base, find out how much time's gone by, or however many things go by, how many times we need to multiply the base on. That's what we're looking for. Put it into that general form from early in the section. Tack up your calculator and go. That is the homework assignment. Now there are a couple problems in here which give you like a couple points and want you to come up with the equation, and that is going to be the second video I'm going to post. Thank you.